Okay guys, sorry I'm not there again today. I wanted to move on with the material just so we're not getting too far behind. So this next chapter, chapter 3, is on something called macromolecules. Now when we separate those two words in the word, macro means large and we know what a molecule is. So macromolecule together literally means large molecule. Now the chapter starts off talking about something called organic. Now when you think about organic, you think about going to the grocery store and you see all these fruits, all these vegetables, and some are priced okay and then some are really expensive. And if you ever notice, those real expensive ones have this symbol on them, meaning they are certified organic. Now usually we're going to find these around our vegetables, our fruits, and our meats. Now if we're talking about the fruits and the vegetables, we're talking about vegetables and fruits that have been grown without any kind of fertilizers and pesticides in the soil. So in other words, the soil can't be like man-made or man-tampered with. And when we're talking about, beef, I know it says grass-fed on there, but when we're talking about organic beef, what that means is there's not going to be any GMOs in it, and there's not going to be any antibiotics injected into the animals. All right. Now, whenever it comes to biology, our definitions of organic and inorganic are going to be a little bit different. So for organic compounds, these are going to be any kind of compound that contains carbon in it. So that's your first big thing, is it has to contain carbon. And then secondly, it has to be found in something living. Now, I know that whenever I showed you the pictures of the fruit, the vegetables, the meat, all of that is going to contain the atom carbon, but they just have a little bit of a different definition on organic compared to what we do in biology. So organic, again guys, it has to contain a C in it. It has to contain carbon if we're looking at the chemical structure of it. And then for inorganic, or not organic, and means not, if we're talking about inorganic, these are anything that does not contain carbon. So for inorganic, if you remember for last chapter, we went over salt, which is NaCl. Na was sodium, Cl was chlorine. Put them together. I know there's a C in it, but that C is associated with chlorine, not carbon. There's no carbon in salt, so we can't say it's organic. All right. So there's your difference between organic and inorganic. Now, moving on from that, we're going to go over what is carbon and why is it so special and why is it the main atom that makes up living things. So when we talk about carbon bonding, if you remember, I'm going to relate this to water. When we went over water, it had oxygen in it and it had hydrogen. Let's focus on that oxygen for the next minute. Oxygen had 6 valence electrons. In other words, it had 6 electrons in its outer shell before it was bonded to any other atom. And that's what we mean by valence. It means just electrons in its outside shell. Now, with the oxygen in water, again, it had 6 valence electrons. It was able to form 2 bonds with 2 different hydrogen atoms in order for it to get its 8 electrons in its outer shell and be happy and be stable. All right. Now, since carbon only has 4 valence electrons, or 4 electrons in its outer shell, it's going to be a little bit different than oxygen. Instead of forming 2 bonds like oxygen did, carbon is able to form 4 bonds because, again, it has to get to 8. So the big thing about carbon is it's able to form 4 covalent bonds. Now, when we're talking about being able to form 4 covalent bonds, in our bodies this is really, really, really good because we can make very large molecules with carbon since it can form so many bonds. Again, the oxygen's only able to form 2, the carbon's able to form a little bit more. All right, and guys, if you're getting behind with taking the notes, again, it's on my website. You guys can look under Chapter 3 PowerPoint, and everything will be on there for you. All right. Okay, so when we talk about carbon bonding, I'm going to show you guys how we are going to make these very large carbon molecules. Now, we're not going to make them as big as they would be in our bodies because they would be absolutely gigantic, way too big for us to put on paper. But just so you guys know, we're going to have three different types of carbon chains, or carbon bonded to carbon bonded to carbon, that we're able to visualize. There's straight chains, there's branch chains, and then there's rings. So what we're going to be making, and I'm going to film another video for you guys on this, is we're going to be making something called hydrocarbons. And I know hydro, you guys think of hydro means water. It usually does. In this example, it doesn't, of course. But in this example, our hydro, like in hydrocarbon, does not mean water, and instead it means hydrogen. So a hydrocarbon is just made of carbon and hydrogen bonded together. So let me show you guys the three different types of chains we can have for carbon. Here was a straight chain. Now if you notice, every single one of those carbons has 4 lines coming out of it. Those lines may be bonded to another carbon, or they might be bonded to a hydrogen. But regardless, if we want to look at the carbon all the way to the left, that carbon has 4 lines coming out of it. What that means is it has made 4 bonds. Now this is a straight chain, and what that means is all the carbons, we're only looking at the carbon for this, it's our most important element for this whole chapter, all of our carbons are in a nice straight line, okay? And that's a little different than the next one. The next one is called a branched one. Now, most of the branched one is going to be a straight line, but there's going to be an area of it where it almost branches off or goes off of the the straight chain of carbons. Now, if you look there, we have 3 carbons in a row, and then on that middle carbon, we have another carbon coming off of it, okay? That's what we mean by a branched chain, right? And then the last one, this is a carbon ring. Now this one looks a little bit different, a little more intimidating than the last two. One, because it's literally in a shape, it's a hexagon. They could be in anything, they could look like a pentagon, octagon, whatever. But for this one, if you're looking at the middle carbon right there, like on the top of the hexagon, you'll notice that there are 2 lines connecting it to the carbon to its right. And what that means is that is a double bond. So if you look at that middle carbon again, that middle carbon, only has 3 atoms bonded to it, okay? And with those 3 atoms, it only, it still has its 4 bonds. So if you look at, again, the center carbon on the top of our hexagon, it's going to be bonded to the H above, that's 1 bond. It's going to be bonded to the carbon to its left, that's 2 bonds, and then that carbon to the right, since it's 2 lines, it counts as 2 bonds, so it does still have the 4 bonds it needs to be stable, okay? These are all covalent bonds, guys, so we can have single covalent bonds, we can have double covalent bonds, and we can also have triple covalent bonds, triple being the strongest of them all. But you got a little experience there with the double bond. Okay, so next thing, with our hydrocarbons, and again guys, I'll film you a video on how to make those, but we're going to make these very large hydrocarbons, and it's not just going to be, after a while, hydrogen and carbon bonded together. We're going to start adding more things into the hydrocarbon. And what we call those things we add on to it are functional groups. Now these functional groups are going to be really, really good for the hydrocarbon because they are going to change some of its properties. They might make it polar. They might keep it how it is originally when it's a hydrocarbon as nonpolar. They might keep it nonpolar. It also might make it acidic or basic. So these functional groups, guys, they're going to determine what it's going to bond with, what it's going to mix with, and whether it's an acid or a base. Okay, we're going to go over 4 functional groups, not too many. In reality, there's hundreds of functional groups, but we only have to go over 4 for the class. So the first one is called a hydroxyl group. And the hydroxyl group is, if you look at the bottom there, it's the 2 elements in blue. So it's the O and the H bonded together. Now that R, the R is like a variable. It's like X in algebra. So the R represents the rest of the hydrocarbon. So the hydroxyl group is just the O and the H bonded together. All right. The goal of the hydroxyl group is to make the whole molecule polar. So we got this large hydrocarbon that cannot mix with water. But once we add the OH to it, it now can mix with water because we turned the whole molecule polar. Our second one is called a carboxyl group. I know it's going to look like there's some similarities between the carboxyl and the hydroxyl from the last slide. There are. It still has the OH at the bottom there, but the difference is it's going to be a C, an O, an O, and an H. So on that C, if you look up top, it's a double bonded O, and that's what makes it a carboxyl instead of a hydroxyl. And what this does is it makes the whole molecule acidic. So if we had a carboxyl group on one end and a hydroxyl group on the other end, it would make it acidic and polar. Okay. Our third one is called an amino group. Again, that R is the hydrocarbon, and attached to that we would have an N with two H's. And what that amino group does is it makes the whole molecule basic or alkaline, right? So it's the exact opposite of the last carboxyl group. And then lastly, we have a phosphate group. I didn't put anything there for like a definition because we're going to see these in the molecule you guys did on your vocab, which was ATP. You're going to see it on ATP, and you're also going to see it on DNA and RNA. It's a main structural component of those three molecules. Now, when we talk about the macromolecules, guys, I know I said from the beginning of this PowerPoint, it was something that is a very large molecule. But in order to get large, there has to be smaller units essentially combining together to make it bigger and bigger and bigger and bigger. So to start off, our smallest unit that makes up our macromolecules is called a monomer. Mono means one. So a monomer is essentially one piece of our macromolecule. Let me relate this to like if you're making a bracelet or a chain link like necklace or whatever. Let me just stick with the bracelet one. We need beads on this bracelet for this example to work. So a macromolecule is essentially like a beaded bracelet where when you have your strings, you put one bead on it. That first bead is a monomer, okay? Now, I know that you'll have a gigantic container, all of monomers, all right? The goal is to get them to join together, like in the bracelet. So it would be like stringing all the beads onto the string. So our first one is a monomer. Once we put our second one on there, our second monomer, we now have two monomers and we combined them together. This makes something called a polymer. So a polymer is essentially more than one monomer bonded together, okay? So that's our polymer. You guys are going to learn that each one of our macromolecules, there are 4 of them. There's carbohydrates, there's lipids, there's proteins, there's nucleic acids. Each one of these is going to have its own specific name for monomers and polymers, okay? And we'll go through them all later on. But as we start to add more monomers, more monomers, more monomers, it's going to get bigger and bigger and bigger and bigger. And once it's done, once your bracelet is done, and you can actually wear the bracelet with all your beads on it, it is then called a macromolecule, all right? Another example of this, guys, would be if we got like, a brick wall. One of our bricks is a monomer. Once we put more than one brick on, it's called a polymer. And once the whole wall was done, that's our macromolecule, all right? So there's your relationship between monomers, polymers, and your macromolecule. As I was going through this, guys, I was thinking, I'm like, okay, something that you guys can visualize a little bit better with things connecting. I know I got the brick wall there, but I was thinking about Toy Story. And I didn't see number 4 yet, but I was thinking about all the different toys in Toy Story. And I finally kind of got something that connects together really well. No, it's not them running on an old-fashioned record player, but I was thinking of Mr. Potato Head looks really weird without a mustache, but I was thinking about the monkeys from Toy Story. And if you have these monkeys, one of these monkeys is a monomer, all right? Now, once we start to put 2 of these monkeys together, I know they're not completely bonded there, but, Once we put the two monomers together, two monkeys together, that's when we get our polymer. All right. Now, after a while, our polymer will grow, get bigger, get bigger, get bigger, and that's when we have our macromolecule. Now, I know, guys, I got 5 monkeys here. You're like, calm, this doesn't make sense. It's like, I got 5 monkeys. You said these macromolecules are huge. They are, okay? In reality, guys, I would not have enough monkeys to make a macromolecule, okay? I would need way too many monkeys. It would fill this whole screen and then some, okay? So hopefully this gave you guys a little introduction to the macromolecules. Make sure you know the difference between monomers, polymers, and the macromolecule, all right? And then start looking over those functional groups. I'm going to film another video for you guys. It'll be on making hydrocarbons, and then we should be good to go. All right, have a good day.